Howdy. I'm fine. Are you online? Ah, okay, fine. I just thought I could. Yes, I just wanted to make sure it's working correctly. Yeah, or now it's in the right place. Me and Michelle Duflo and Joseph Wolf. Hang on, give me a second. What happened here? Okay. Just hang on the phone for a second because I want to make sure that this is working correctly. There we go. Did David just join? I do. There we go. All right, and you're looking at the Atlas thingy. Mute exactly.
Hi, David. Good morning.
Good morning, Kyo. That's a beautiful background you have, but I guess it's China and not Japan. Is that, or is it entire? It's entirely imaginary.
Oh yeah, it's from Star Wars.
Ah, yes, yes, yes. Okay.
Your background isn't bad either.
Oh, thank you. Oh, I meant to change it though. Let's see.
Okay. Not bad.
No, not bad. We're more distant than it appears. The other meeting that I just came from was MIT faculty meeting where they were reading citations of all retiring faculty. On on the average, I invented the internet, got 2 Nobel Prizes. I forget that there was a lot of good stuff there.
You ain't heard nothing yet.
Yeah. You know, Jeff, that there's a non-mathematician on the participant list?
Oh, yeah?
Yeah.
Hello.
R. Adams. Hi, Annegret.
Hi, David.
R, oh, excuse me, R. Adams, yes.
Yeah.
Hello.
Hi, everyone.
Hey, Mel. Hey, Sue.
How are you?
I'll be back in 1 second.
David.
Everyone's keeping safe.
So Susanna, your Zoom window doesn't know yet that we're supposed to call you Sue. And probably I will never learn, so it's okay.
I don't know how to change my name from here.
That's what children are for.
Yeah, I have to ask Sonia. She will tell me. But I have to change my name from so many places. I have one or two at a time.
Susanna, hello.
Hey, hi, Jeffy. How are you?
I understand you're retired.
I did. Yeah.
When?
Last January, January ago, a year, 2019.
Uh-huh.
Yeah. Are you retiring soon, Jeffy?
Nope. Not until the Atlas project's finished.
Oh. You know, one thing doesn't have to prevent the other from happening.
Are we going to get a report on how long till the Atlas project is finished?
No. I wish I knew.
Just say mañana.
Oh, so I forget, David, you said there's a, I forgot, there's an MIT tradition or something that it's really, the starting time is something different?
4:35. Yes,
4:35, okay.
that's right. Oh, and the I'll watch the participant list, and when the curve of participants flattens a bit, then we can.
I think we lost Bill. I thought he was already here.
He's
I'm
still
here. I'm still here. I
Oh,
just muted myself, but I'm here.
oh, okay. Oh yeah, I know what happens. You cannot see everybody.
Thank you, Lentong. That's wonderful.
I mean, I can show my video, but I thought it would be better just to.
That's better.
When I was looking at conference pics today in order to find the Jeff background, the best of the conference pics was Monica, but I was making the choice on mathematical grounds, not aesthetics.
Where's the picture from?
It's from my 60th birthday conference.
Ah.
Can't you tell by the shirt? I mean, I keep shirts for 20 years, but other people I hear don't do that.
No, but Greg Zuckerman could tell me when I was wearing that shirt.
Yes. Yes. Okay, I'm very pleased to have my longtime friend Jeff Adams from the University of Maryland giving our last Lee Group seminar talk about unipotent representations.
Thank you, David. So thank you very much for the invitation. It's a real honor of the highest order that you've asked me to give this last lecture in the Lee Group seminar before you retire. I'm going to be lecturing about the Atlas of Lee Groups and Representations project. In particular, I'd like to talk about unipotent representations. It seems appropriate, since this is the last seminar of your long, illustrious career, that I thought I should pay you some tribute, but I don't feel up to the task. And so instead, I had the following idea. I got a group of about 30 of David's longtime collaborators together last Friday, and we had a Zoom session together, and everyone shared their appreciations of David. And David, I'll send you the this video. Actually, it's in Dropbox. I'll make it available to you. It was a really wonderful experience. It was great to see everybody, and it was great to have an opportunity to hear about David. We also did a session with David's students, and we'll also send that to you. Excuse me. And I want to give a shout out to my son Joshua, whose idea this was. Okay, so the Atlas project it's a long-running project to use computers to study representation theory. And here's a list of the people that have been involved over the years. And I want to start off by talking about the unitary dual. And I wanted to say one other thing before I begin. I thought the best way that I could pay tribute to David would be to talk about some of the wonderful mathematics that he's been involved with over the past 40 years. And that's largely what this talk is about. And I think it's fair to say that all of the deep ideas that I'm going to talk about today are due to David. So I realized right away I've made a mistake, but so be it. Actually, give me 1 second. All right. I have to fix one small thing. I knew this was going to happen. This will give a few more people to join. Okay, let's try that again. There we go. So I'm going to talk about the unitary dual. So G is a real reductive group. So think the general linear group GL and R, perhaps the symplectic group, or of course the split group of type E8. And the problem is to compute the unitary dual G hat of G, the irreducible norm preserving representations of G on a Hilbert space up to isomorphism. Lie groups and their representations are ubiquitous in mathematics, physics, and other areas, and the unitary dual is really a central object in mathematics. This problem of classifying it goes back to Hermann Weyl in the 1920s. The answer is not known in general, certainly. Here are a few cases which are known. Weyl completely understood compact groups. And so in 1947, Bargmann computed the unitary dual of SL2R. The general linear groups over R, C, and H were done by Vogin in 1986. And complex classical groups by Dan Barbash in 1989. Those are those two are infinite families of groups. In 1994, David computed the unitary dual of G2, which is a single group, but extremely complicated and quite an achievement. And it's well known for a long time that the answer to this question, the description of the unitary dual, is very complicated in many cases. The Atlas of Lie groups and representations is based on the following theorem of Vogin from the 1980s. For any given group G, there exists a finite algorithm to compute the unitary dual. Now, this is a rather weak statement. There exists a finite algorithm. In a sense, I think the most accurate thing to say about this algorithm is that David, given any particular group and enough time, can in principle calculate the unitary dual. But there's a serious question here, which is this a result of more than theoretical interest? To know that there's a finite algorithm to compute something is quite useful, but is it practical? In other words, can this algorithm be made explicit and implemented on a computer? This was an idea that we kicked around for many, many years and didn't take seriously until the early 2000s. And the Atlas of Lie groups and representations is basically based on the following idea from 2002. Take this question seriously. See if it's possible to implement this algorithm and actually compute it. Besides the unitary dual question, there are many, many other questions in representation theory that we're interested in, of course. And we're equally interested in providing software for the mathematical community. We want to provide software for people to use to study representation theory and also to teach representation theory. And in some sense, one of the most important reasons we're doing that I'm doing this is the sort of principle that I only really understand something if I can implement it on a computer. I'm not sure how widespread or how popular an idea this is, but I think it's quite a useful one. And I can't tell you the number of times when I read a paper and I thought I understood it until I tried to implement it and I realized I didn't. And so the Atlas project is taking that idea to extremes. Excuse me. Okay, so I'm going to give the outline of this talk is I'm going to give a brief overview of the Atlas algorithm and then some applications to unipotent representations. Excuse me. And maybe I'll pause here, David. I don't know, it's a big audience and I don't know how questions work, but if people want to interrupt me, that's okay.
So anyone can unmute herself by pressing the space bar. And I think that's probably the best thing to do. I don't have anybody to watch the chat window for questions there. So I think interrupting is the tradition of the Lie group seminar, so that'll work just fine.
Good. Hopefully I'll get interrupted at least once by the end. So.
Well, you can't count on it.
Is Kajdan here?
No, but
Sorry.
I'm here.
Ah, very good. Okay, good. So GK modules. Harishchandra reformulated the question algebraically in terms of GK modules. So G naught is the Lie algebra of G. Complexification is G, and K is a maximal compact subgroup. And an admissible GK module is an algebraic representation, pi V. So that is to say, V is a complex vector space with no topology. And it's a representation of both G and compatibly K. The admissible dual of a Lie group, of a real reductive group is known. That's due to work of Langlands, Knapp, Zuckerman, and Vogin. We say that an irreducible representation GK module is Hermitian if it, well, the natural condition, if it preserves a non-degenerate invariant Hermitian form. That is to say, there's a Hermitian form on the vector space, written angle brackets, with this invariance condition for the action of the Lie algebra, and also the natural invariance condition for the action of K. Finally, we say the representation is unitary if this form is positive definite. And a deep result of Harichandra's is that there's a bijection between the unitary dual of G, which is to say the norm-preserving representations on a Hilbert space, with these algebraic irreducible unitary representations up to the appropriate notion of equivalence. So we can leave analysis behind, and we're now purely in the world of algebra. So the groups that we're interested in are the following. You take a connected complex reductive group, G of C, and we suppose that it's defined over R, and we take our group G to be the real points of that. So I have to apologize to Roger Howe for this. It doesn't include the metaplectic group. Here's the main result of Atlas, which I'm going to talk about today. Suppose pi is an irreducible admissible GK module. Then there is an explicit computable algorithm to compute the signature of the invariant Hermitian form on the space, and in particular to determine if that representation is unitary. Okay, so a word here about attribution. I've attributed this theorem to Atlas. This is a little bit in the Bourbaki philosophy, which is that this is a large collaborative project, and it's not generally possible or not even desired to parse the credit. So I'm just going to say most of these results are due to Atlas. This algorithm has been implemented in the Atlas software, of course. Now, this particular reference, this particular result has finally appeared. And here's the reference. It's an asterisk, volume 417, and this should be appearing shortly. It's also available on the archive. You look it up under this title. And the archive dates from 2012. So it's taken a little while, but it's about to appear. Okay, so let me expand a little bit on what I'm talking about. So the notion that an invariant Hermitian form on an infinite dimensional vector space is positive definite is perfectly well defined. It's that every vector has positive length. But what does it mean to compute the signature of a Hermitian form on an infinite dimensional vector space? That's not clear that that notion is even well defined. Never mind, what does it mean to compute it? Well, in our setting, here's what it means. This representation pi, if you restrict it to K, it breaks up as a direct sum of irreducible representations of K, each of which is finite dimensional, and each occurs with a finite multiplicity. That's the admissible assumption. So you have this decomposition, and the sum is orthogonal with respect to the Hermitian form. And on the on the mu isotypic subspace, the copies of mu, the form is positive on each irreducible of K. So, excuse me, because K is compact. So it's going to be positive definite on a certain number of copies of mu and negative definite on others. Call that P and Q, where P plus Q is the multiplicity. So we can record this information as follows. We define the ring W to be Z bracket S, where S squared is equal to 1. And we define a signature function given a representation pi. It's the map from K hat to W, where the value of the function on mu is the element P plus QS of W. where P and Q are given on the previous slide. Where P comma Q is the signature on the mu isotypic. So the S is just sort of a placeholder to record the negative part of the signature. So formally, you can write that the representation pi together with its form is an infinite sum of these signatures times mu. And this is a generalization of the preceding formula about the multiplicities. Another way to say that is that the signature function is a refinement of the multiplicity function. If you take the signature function of mu and evaluate it at mu, that's an element of W. If you then evaluate that at S equals 1, you get P plus Q, which is the multiplicity. So this formula here is a refinement of the one on the previous slide. So here's a theorem of David's from the 1980s. Suppose pi is an irreducible admissible representation. Then there are finitely many irreducible tempered representations pi I and elements wi in the ring such that we have the following identity. The signature function of pi can be written as a finite linear combination of these multiplicity functions with coefficients in this ring W. So let's pause and parse what that means exactly. Before I do that, let me say, and the consequence of this is that the representation is unitary if and only if all of those wi's are integers or all of them are s times an integer. Because if they're all integers, it's positive definite, and if they're all s times an integer, they're all negative definite. It's negative definite, excuse me. All right, so let's parse this, this equation for a minute. It takes a little thought. One way to say it is that these signature functions, which are maps from this infinite set k hat to W, well, there are some other functions like that, which are the multiplicity functions of the tempered representations. And I'm saying that the signature functions are in the finite W span of the multiplicity functions. Or another way to say it is the following. This is a little bit more concrete. It says that if you give me these numbers, these elements wi, you can compute the signature function on a k-type by as follows. You run over all of the pi i's and you take these multiplicities, those are integers, and you multiply them by these ring elements wi. That gives you a number of the form a plus bs, and that's the signature. Implicit in what I said above is these tempered representations are unitary. And these functions, multiplicity pi I, are known. And so remember, what this is these are the k-type multiplicity functions. And I put known in quotes because this is one of many places in Atlas where there's some math which is considered known, but the difference between that and actually computing something is gigantic. And in particular, these compact groups who we're talking about K are disconnected. And so you can't just use the theory of highest weights. You have to deal with disconnected groups, and it's highly non-trivial. One of the main things that Atlas does is compute them. Atlas computes these multiplicity functions for multiplicity sub pi for any pi, tempered or not. And that's a whole talk in itself, but I'm just going to leave it at that. Okay, so let me go back a little bit. I've spoken a little bit loosely about these Hermitian forms. You might ask yourself, well, suppose pi is an irreducible admissible representation. Does it have an invariant Hermitian form? I've kind of been implying that it does. And if it does, is it canonical up to sign? So it is easy to see that if it has an invariant Hermitian form, it's unique up to real scalar. And since we're concerned with signatures, the only thing that matters is the sign. So we'd like to know if this signature, this is a reasonable thing to ask, is that it'd be canonical up to sign. Well, the answers are no and no. what I mean to say more precisely, of course, is that not always. Some representations don't have an invariant Hermitian form, and it's not always canonical. So from now on, I'm going to restrict, it's a technical restriction to the case of integral infinitesimal character. That is to say that the Harishchandra parameter is contained in a particular real subspace. And there's a natural reduction. If you're studying unitary representations, there's a natural reduction to the case of real infinitesimal character. And the attribution I've put here is Vogin and Knapp. And what this arrow means is to indicate the kind of thing that I have to deal with these people, which is that according to Vogin, this result is due to Knapp, and according to Knapp, this result is due to Vogin. So in any event, you can read about it in Tony's overview book.
Can I ask a question, Jeff?
Sure.
Yeah, so what do you mean by saying it may not be canonical?
I'll illustrate that on the next slide.
Uh-huh.
So Knapp and Zuckerman computed this Hermitian condition. So this is a subset of the admissible dual. The question is which of the representations there support an invariant Hermitian form, and they did this. Here's the theorem of Atlas. You let theta be the Cartan involution of the Lie algebra, or of the group, I should say. Then pi is Hermitian if and only if pi upper theta is isomorphic to pi. So what that means is that theta is an automorphism of the group, and it's an automorphism of everything in sight, the complex group, the complex Lie algebra, and it fixes K, and therefore it acts on the space of GK modules. And the representation is Hermitian if and only if it's fixed by this action. In particular, every representation of an equal rank group is Hermitian. Now I mention this because I view this as one of the first successes of the Atlas project. What happened was we wrote software to compute this Hermitian condition, and we noticed that that in our equal rank groups, our favorite examples like the symplectic group, every representation turned out to be Hermitian, and we didn't know why. And at some point we recognized this, and once you've made this observation, it's a very simple proof. But and Knapp and Zuckerman could have, and anyone else could have made this observation in the 1980s, but they didn't. And we spoke to all of the experts, and nobody had recognized this. And well, I think this is one of the things that software is good for. It pointed out something that we hadn't observed before. And this is just a reminder, everything I'm talking about here is real infinitesimal character. Okay, so here's an illustration of this question about whether the form is canonical. Consider the group SL2R and the principal series with odd K-types. So that's a family of representations. The K-types, the representations of K, which here have multiplicity 1 and are parameterized by the odd integers. And take the infinitesimal character to be real, and let's say between 0 and 1. Then it's a simple fact that this representation does support an invariant Hermitian form, but it has opposite signs on the two lowest K-types, plus or minus 1. And what that says is that there's no canonical way to prefer one of the forms versus its negative. And one of the first things I learned thinking about this stuff and talking to David was, you might think that you can prefer 1 versus minus 1, but there's an outer automorphism of SL2R, which acts by inverse on K and exchanges those two lowest K-types. So there is no intrinsic way from the group to prefer one of those forms over the other. Okay, so recall the definition of the invariant form is this. This is the invariance property on the Lie algebra. And the experts in the audience wince a little bit when I write this because X here is in the real Lie algebra, and GK modules, one of the basic ideas is that you should only talk about the complex Lie algebra. Well, let's do that. What's the formula for the complex Lie algebra? It's this, where the formula now on the second term here, sigma on X, you put in sigma of X, where sigma is the anti-holomorphic involution of G whose fixed points is G naught. And you need that formally just to preserve the Hermitian property. The bar is pulling out in the right way. So that that's the correct notion of Hermitian. And in, I mentioned these WIs, and in small examples, it's possible to explicitly compute them, but because of this issue that I just mentioned, the fact that the Hermitian form doesn't always exist, and even when it does, it's not canonical, it basically makes it impossible to formulate a general algorithm. If you try, you just very soon run into a problem, like every time you come up upon a representation, you have to decide which form do you want to put on it, and before you know it, you're lost. The key idea to resolve this is the following. It's to use a modification of the invariant form. That's called the C form. And the definition is the following. A C form on a representation is a Hermitian form satisfying the following invariance condition. So it's exactly like the one I just wrote, except that I've replaced sigma with sigma C, where sigma C is the compact real form of G. It commutes with sigma, and its fixed points is a compact form of the complex group. Now, this is kind of a funny formal object. The sigma C is not sigma, so this doesn't directly have to do with unitary representations of G, but formally it's a perfectly good definition. And given that, we define the C signature of a representation just as before. We say that the C signature of mu is P plus QS, according to the signature PQ of the C form on the mu isotypic subspace instead of the ordinary Hermitian form. So I mentioned it's not really possible to formulate a precise algorithm directly to compute sig pi. Well, here's what I view as the big theorem of Atlas, and I like to call it life is beautiful. Suppose pi is an irreducible representation with real infinitesimal character. Then an invariant C form exists. So unlike the ordinary emission form, it always exists. Secondly, it's canonical. You can choose it to be positive on all lowest K types. And furthermore, there's an explicit formula relating the ordinary C form, the ordinary Hermitian form and the C form. So without the point of this last statement is it's fine to talk about the C form, but at the end of the day, we want to compute something about the ordinary Hermitian form. Well, that's fine. There's a formula relating them. So it's at least possible to formulate an algorithm to compute the C signature, and therefore, by the third bullet, the ordinary signature. So what we want is a formula for the C signature, analogous to the one that I wrote down earlier for the ordinary signature, and a way to go from one to the other. So briefly, here's the main step in the algorithm. Every irreducible representation is the unique irreducible quotient of a standard module, or IP sigma nu. So P is a real parabolic, sigma is a discrete series, nu is a character of the split torus A, and which is identified with an element of a complex vector space Cn. The condition of real infinitesimal character is that nu is contained in Rn, a particular real subspace. And the tempered condition is exactly that nu is equal to 0. Now, this family of representations, if you fix P and sigma and just vary nu, they can all be realized on the same vector space V. So let's fix that. And what you get is a family of Hermitian forms parametrized by this parameter nu. And you can look at how that those forms change as you vary nu. And it's a basic fact that the signature can only change. I said the the form only changes. What I mean to say is the signature only changes at finitely many reducibility points. And at a reducibility point, the representation has a natural filtration called the Janssen filtration. And the basic principle is that when you deform the form through a reducibility point, the signature changes on odd levels of the Janssen filtration. And that's basically the fact that the polynomial x to the n changes sign at 0 if and only if n is odd. That's really more or less what it comes down to. So the idea is to deform nu to 0 and keep track of the sign changes as you do. And eventually you get to a tempered representation. I mentioned that those are unitary. And so all the signs are positive. That's a slight, that last statement is not quite, I shouldn't have included that. At nu equals 0, the representation is tempered, and we know the signature of the Hermitian form on it. Of course, it's positive definite. So here's the main deformation formula from the asterisk paper, or see the archive. It looks like this. And I'm not going to try to explain this in detail, but I just want to sort of put it up there and show you how explicit it is. It says that if you deform the signature from 1 plus epsilon nu to 1 minus epsilon nu through a reducibility point, the way the signature changes is controlled by this formula. And the ingredients in the formula are, well, these L naughts, which are some technical thing, just some integers. And the main thing is these P's and Q's. These are the Cauchy-Schoenlistic-Vogel polynomials. These are polynomials in an indeterminate Q. And here they're evaluated at S, Q equals S. And the last term is the C signature on another standard module. And this formula is inductive in that the terms which appear on the right-hand side have smaller nu. And you can apply this recursively. You can send nu to 0, and you eventually get a computable formula for the signature of a standard module in terms of these multiplicity functions of tempered representations. Now, obviously, this is extremely complicated. It's not suitable to human calculation, but it is well suited to computer calculation, and this is what we've implemented. Now, the last step is you can express an irreducible representation as a linear combination of standard representations. That's part of the standard theory. And that goes with these, along the forms. There's a formula which involves the form also. And so you can write the formula for the signature on an irreducible in terms of a linear combination of standards. And then finally, I mentioned earlier, there's a formula relating the C form and the ordinary form. Well, in the equal rank case, it takes the following form. The ordinary form and the C form are related by this formula. There's a fixed root of unity out front, and there's an element of K, which appears inside.
Jeff, can I ask a question?
Sure.
Yeah. What on the previous slide you had L of tau and L0 of tau. So could you explain what is the difference between those? Is there some length of?
Yeah. So yes, that's two different things. So L is the ordinary length, and L0 is a technical thing that we call the orientation number, which has to do with, which only plays a role when the infinitesimal character is non-integral. And it has something to do with crossing walls which are with non-integral roots. But the L is the ordinary length, and L naught is this other technical thing.
And this difference L naught of gamma minus L naught of tau is always even.
It is.
Mm-hmm. Only when the difference of L's is odd, or always?
No. So what's true is that if gamma and tau are in the same block, which means that they have the potential to appear in a formula like this together, then the difference is even.
Okay. Thank you.
Okay, so, well, there's an enormous amount of mathematics which I've swept under the rug here. And I just want to point out one thing, which is I mentioned this formula in the equal rank case, the one just on the slide there. In the unequal rank case, you need to extend the group K to an extended group where delta is the action of acts by theta. And this element X, which is there, is an element of the extended group. And this requires the twisted Kajian-Lustig-Vogel polynomials, which were studied by Lustig and Vogel in 2014. And they're a major technical aspect of the program, but I'm not going to talk about them more here. Okay, so that completes my lightning overview of the ATLAS algorithm and project. And we more or less completed the calculation that I just sketched about 5 years ago. And since then, we've been going on to use it to study all sorts of interesting things. In particular, let's consider the most interesting unitary representations. So for that, these are the unipotent representations. So let gamma be the Galois group of C over R. G is our connected reductive algebraic group. Check G gamma is the check G is the complex connected dual group, and check G gamma is the L group. It's an extension of the dual group by the Galois group. This is what's sometimes written LG, but I'm going to call it this. And we consider the following thing. You look at homomorphisms from SL2C cross gamma into the L group, which make this diagram commute. So these are the parameters which Arthur introduced and are now called unipotent Arthur parameters. And Arthur made a conjecture in 1983 that associated to such a parameter is a finite set, pi psi, of irreducible representations which are now called unipotent. He did not define these packets, but he gave some properties which they should hold. In particular, these packets should contain a certain tempered L packet, which he described. The infinitesimal character of
Sorry, the word tempered should be replaced by Langlands.
Sorry, that's correct. That's a misprint. A certain possibly non-tempered L packet, excuse me. That's correct. And the representations have a prescribed infinitesimal character. Many of you recognize this as the one associated to a nilpotent orbit by the Dinkin classification. And if you take the distribution characters theta pi, as pi runs over this packet, that's supposed to contain a stable character. And the representations in an Arthur packet are supposed to be unitary. Now, Arthur made this conjecture in the setting of automorphic representations. So I've stated it over R, but it's local and there's also a global version. And he predicted that these representations are the building blocks in a precise sense for the general automorphic representations. Locally, in our setting, we expect that the unipotent representations are expected to be the building blocks of the unitary dual. Okay, so what is a unipotent representation or unipotent packet? As I said, Arthur didn't give a definition. He just made a very visionary conjecture about their existence. The terms unipotent representation packet have come to mean many different things over R and over local and global fields, not to mention over finite fields, where there's a lot of work of George Lustig. In particular, I'd like to single out Dan Barbash, who's done a lot of work on various notions of unipotent, which generalize the one that I'm about to talk about. in general, they're not precisely defined. And for more of a discussion, there's what we called Vogan's Orange Book, Princeton University Press book, for a further discussion at this point. So today I'm going to, well, in the Atlas project, we focus on, of course, the RILs and what is a well-defined notion of Arthur unipotent, of unipotent representation or packet. Sometimes these are called Arthur unipotent, or sometimes special unipotent representations. So this is an important special case, very close to Arthur's original conjectures. These were originally defined by Barbash and Vogan in 1986 for complex groups, and then in the book by Adams, Barbash, and Vogan in 1992 for real groups. For today, I'm going to precisely define something slightly weaker than an Arthur packet, which is, we call a weak unipotent Arthur packet. It's natural to ignore the gamma. So suppose O check is a unipotent orbit. Then we define the weak Arthur packet associated to O check to be the union of the Arthur packets, where you run over these parameters psi from SL2 cross gamma into the L group, where psi restricted to SL2 corresponds by the Jacobson-Morozov theory to the orbit O. So you fix the restriction to SL2C, and you get a finite number of possible extensions by looking at gamma, and that's a weak Arthur packet. And it only depends on the orbit. And it turns out it's easier to describe these weak packets than the honest ones. So I'm going to do that. What you do is in the book, in the 1992 book, we gave a precise definition of an ordinary Arthur packet. And if you apply that to these weak packets, it simplifies and looks essentially like the Barbash-Vogan definition. And here's the theorem. The weak Arthur packet associated to a complex nilpotent orbit O check is the following irreducible representations of G. First of all, the infinitesimal character is the one predicted by Arthur. I've written lambda O check. And the second condition is a condition on the associated variety of the annihilator of pi. So let me explain condition 2. D is Spaltenstein-Barbash-Vogan duality, which takes unipotent representations of G check to unipotent orbits of G check to unipotent orbits on G. The annihilator of pi is An of pi is the annihilator of pi in the universal enveloping algebra. Associated to that, by taking the associated graded, is the associated variety of the annihilator, which it turns out is the closure of a complex unipotent orbit. And so the condition for condition 2 is you run over all of the representations with the given infinitesimal character whose associated variety is prescribed by this formula. And then by definition, or I called this a definition, but it's a corollary. The unipotent representations by U of G are exactly the union of the weak Arthur packets. And I'll just make a remark here. The honest Arthur packets have a similar definition, but they involve a finer invariance called the associated variety of pi in place of the associated variety of the annihilator. And I'm not going to say more about that. So here's the theorem. There's an explicit algorithm to compute weak Arthur packets. For a given orbit, you can compute pi of O check, and therefore the unipotent representations of G. This algorithm has been implemented, past tense, in the Atlas software. Given G in an orbit O check, we compute an explicit list of Langlands parameters of the representations in this Arthur packet. So, of course, one of the first things we did in the Atlas software is implement the Langlands classification. So we describe representations in terms of their Langlands parameters. And in order to specify an Arthur packet, we specify a collection of Arthur parameters, or Langlands parameters, excuse me. So here are the ingredients of this calculation. Of course, we need the unipotent orbits in the dual group. We need to compute the centralizer of the centralizer of the SL2. This is a disconnected reductive group and is a little bit tricky. We need to compute the action of the Weil group on the Grothendieck group of virtual GK modules. We need the Kazhdan-Lustig-Vogin polynomials. We need to compute cells in the Grothendieck group, which comes from the KLV polynomials. We need to compute special representations of cells. We need to compute duality of nilpotent orbits. And we need the Springer correspondence. There's a tremendous amount of mathematics which goes into this, and all of this has been implemented in Atlas. And the star is indicating that only this last bullet requires tables. Everything before that is computed de novo for an arbitrary reductive group. And that's an important point because that's really the way you need to be able to do that. You need to be able to handle an arbitrary reductive group for lots of reasons, in particular for all of our inductive arguments. It's certainly not enough to just think about simple groups or anything like that. Okay, so here's an example. Here are the unipotent representations of all of the real forms of exceptional groups. So this was computed by Atlas. So for example, G2 has two real forms. The compact real form always just has one unipotent representation, which is the trivial representation. And the split real form has 12, it turns out. F4 split has 75. We have both the simply connected and adjoint forms of E6 and E7. And finally, E8, of course, the most interesting. E8, the split form of E8 has 362 unipotent representations. The quaternionic form has 57, and of course, the compact form just has one. There are lots and lots of fascinating things to see in this table. Of course, the split groups or quasi-split groups have the most unipotent representations. I was a little bit surprised that the other forms, the numbers go down so fast. For example, the quaternionic form of E8 only has 57 compared to 362 for the split form. But there they are. So I want to pause here and make a comment. I remember as if it was yesterday, the day in 1983 when I was at MIT and David walked into my office and he had just been at a conference at the University of Maryland and he was super excited about a talk that he had gone to by Jim Arthur, where Jim first spelled out these conjectures. And I give David a lot of credit. He was very excited to talk about this. I don't think I really knew what he was talking about at the time, but his enthusiasm was certainly infectious. And a few years ago, I was on a flight to Asia, and I had my yellow pad, my pad of paper, and I was doing a calculation, and a young guy next to me asked me what I was doing. And I said, I'm a mathematician, I'm working on a math problem. And many hours later, when the plane started to land, he looked over and I was still writing. And he turned to me and he said, "You're still working on the same problem?" And I just said to him, "You have no idea." And here we are 40 years later, and I can finally tell you what the unipotent representations of the exceptional groups are. And we're quite happy about that. Okay, so here's an example. This is G2. G2 has five complex nilpotent orbits listed there. And there are their dimensions and lots of information about them, the Levy factors and centralizers and component groups and so on. And here at the end is the list, or the numbers of unipotent representations, 2, 2, 2. The weak packets are of size 2, 2, 2, 5, and 1 respectively. And what these last equations mean is that, in fact, in this case, we know the honest Arthur packets. If you look at this column here, the number of Arthur packets for each orbit is listed. And in this case, the honest Arthur packets are disjoint. And each of these weak packets is a sum of honest Arthur packets according to these numbers. I should have mentioned earlier that Arthur packets are not in general disjoint, one of the things that makes them a little bit interesting and complicated. And here is the actual list of representations. So I don't want to explain this except to say that we know them on the nose. This is the Atlas version of the Langlands classification, and so we know precisely the unipotent representations associated to each of these 5 orbits. Okay. Of course, I'm giving a talk at MIT, if just virtually, and I couldn't possibly do so without showing you E8. E8 has 70 nilpotent orbits, unipotent orbits. And here are the numbers of unipotent representations associated to them. The size of the weak packets are in this column. And there's tons and tons of fascinating information in these tables. For example, I'll mention this column here. These centralizers are disconnected groups, and it's important to know the precise structure. And sometimes these extensions split. This here the bar indicates this is a semi-direct product, but sometimes they don't. And I believe that all of these details, well, I know that all of these details have implications for these unipotent packets, and I'm sure that they do for the global theory of automorphic forms as well. And this is the second column. This is the second page of the same information. And I want to just look at one example. Again, George Lustig, I believe, is attending, so I have to mention this orbit whose centralizer is S5. And it turns out that there are 18 unipotent representations associated to this orbit, and they break up into 3 disjoint Arthur packets of size 7, 6, and 5, respectively. And here they are. And it turns out that the size of these Arthur packets has to do with the number of irreducible representations of the centralizer of the parameter. And so when psi of j is the identity, the centralizer is S5, which has 7 irreducible representations. That's one packet. And the other 2 things which occur are S2 cross S3 and the dihedral group D4. And the numbers work out perfectly. And I have to say, the thing that really impresses me is after all this time when we write this software and we get these answers, it's exactly as the experts George Lustig and David Vogan and others predicted. It's amazing to me. Okay, let me talk a little bit about unitarity. It's well known that every representation of GLN, R, or C is unitary. That's from David's paper. And Jim showed the same result for the orthogonal and symplectic groups. And so that raises the question of the exceptional groups. And of course, I can't tell you anything about fields besides R. But here's a theorem due to Atlas and together with Stephen Miller and Joe Hundley. Every unipotent representation of a real exceptional group is unitary, with the possible exception of 4 representations of the split form of E8. So that's these, where are they there? These 1,465 representations. We know all of them are unitary except for a few. And here's a sketch. Well, Miller and Hundley have showed that some of these representations occur as L2 residues of Eisenstein series and are therefore unitary. If the orbit on the dual side is not distinguished, there's a natural reduction to a Levy factor, real parabolic or cohomological induction. And the Atlas author, as I mentioned, can compute unitarity. However, for these few representations of E8, it's not, for some representations of E8, it's not possible to run the software due to problems of time and or memory. We have a number of different techniques which overlap. And so they sort of work as checks against each other. And when you put them all together and you spend a lot of time, you get everything you can. And what's left is these 4 representations of E8 that we have yet to prove are unitary. Okay, I wanted to pause just for a second there. And I can't let this opportunity pass to not at least show people briefly the Atlas software. So I believe I'm sharing my screen with the Atlas software in it. Is that correct?
Yes, indeed.
Thank you. So I'm going to set G be F4S, the split real form of F4. And I'm going to set unipotent to be the unipotent representations of G. So this is implementing this algorithm, which I've discussed. And it's running over all of the orbits on the dual side. And it's telling you a little bit of information as it goes. And it's computing the collection of unipotent representations of split F4. Let's see how many there are. So I think this takes about 30 seconds. There we go. How many are there? 75. That's the number that I appeared on the previous slide. And let's check that they're unitary. They are, every single one of them. Pretty nice, huh? Okay. So I'm going to conclude with a couple of conjectures. Conjecture 1, every Arthur packet comes equipped by definition with a map to the representations of this of the component group of the centralizer. And R is the finite dimensional representations, not necessarily irreducible, of this finite group. And the conjecture is that for a unipotent parameter, this is a general statement about all Arthur packets, not just a unipotent one. The conjecture is that for a unipotent parameter, this is actually gives you a bijection, which is to say the image of this map actually consists of irreducible representations. That's not clear. And it's a bijection. This is known to be false for more general non-unipotent packets, but we know of no counterexamples to the conjecture for unipotent packets. On the other hand, we don't have any idea why it should be true. So that's something we'd like to check. And I'm going to conclude with a conjecture about tempered unipotent Arthur packets. You can ask the natural question, when does an Arthur unipotent packet consist entirely of tempered representations? Well, very roughly, you would think never. The whole point of the SL2C factor that Jim introduces to account for non-tempered representations. Well, okay, there's the case when the parameter restricted to SL2C is 1. That's a very special case. So here's a proposition which is not difficult. First of all, if G is split, then the Arthur packet associated to a complex orbit on the dual side is always non-empty. All of these packets are non-empty. And consider the 0 orbit on the dual side. So by duality, that corresponds to the principal orbit on the group side. Then this Arthur packet is non-empty if and only if G is quasi-split, in which case it's precisely the representations of infinitesimal character 0, and these representations are all tempered, as they should be, because the psi restricted to SL2C is trivial. By the way, 2 weeks ago, I think in the seminar, Lucas Mason Brown gave a talk where he talked quite a bit about this particular example. So here's a conjecture. The Arthur packet associated to an orbit consists entirely of tempered representations, if and only if O check is the minimal orbit for the real group G for which this packet is non-empty. So this is true for G split or quasi-split by the previous proposition, because in that case, the orbit in question is the zero orbit. It's true for compact groups, duh. And we've observed that it's true for all real forms of exceptional groups, case by case. And this is one of these things where I just, after we computed these, I made this observation, and I mentioned it to David. And usually when we observe something like this, David has an explanation. Oh, it's because the orbit's normal or something, and Kazhdan-listed polynomials are all one, or who knows what. But we don't know if this is true, and if it is, we don't know of a good reason. And I'll just conclude with an illustration of the idea. Here's the beginning of the table for E8. So in this column are the sizes of the weak packets for these nilpotent orbits of E8, starting with the zero orbit. The zero orbit has 3, a packet of size 3. And all of these numbers are non-zero. The group is split, so all of these packets are not empty. On the other hand, the zero orbit does not have any support any unipotent representations for the quaternionic form of this group, because that's in the lemma. It's not quasi-split. And as a matter of fact, the whole bunch of orbits at the beginning don't support any. This orbit, this is the first orbit for the quaternionic form, which supports unipotent representations. There are 2 of them, and here they are. And nu is 0 for both of them. I would dearly love to understand why that is. And we have more work to do. And with that, thank you, David. And if I can, I will now go to the tail end of our video.
Thank you very much, Jeff. Are there questions for Jeff?
Yes, Jeff,
Yes, Greg.
hear me?
Mhm.
Okay, you don't need to see me, but you can hear me.
I can picture you, Greg.
Uh-huh. So I always thought that the tempered representations were the ones that we understood the best. So you're ending with a kind of a paradox, but you still have questions about tempered representations in relationship to this theory of unipotent representations.
Absolutely. That's a very interesting comment. I mean, if you look at the way these tempered representations appear, they're I don't know what to say. They're few and far between, and we don't understand them.
I mean, you can describe each one of them independently
Of course.
as a unitary representation.
Right. I'm right. Each one of those representations, in a sense, is boring. We know what it is. It's tempered, but it plays an interesting role in automorphic forms.
Okay.
Have you tried to make sense of the other tempered representations that appear in the unipotent packets? Are there? Yeah, there are others, aren't there? Or are there?
Yes. So actually, you remind me when I made a statement which was slightly too strong. I stated a conjecture, and I said that it's true for split groups. The only if part is only a conjecture, which is to say, for some groups, for example, a split group, there are Arthur packets which contain some tempered representations, but not all. And that's also something that we don't understand very well.
Other questions?
So Jeff, how does this story change if in the beginning we assume we have a disconnected group G?
That's a good question. I couldn't see. Who asked this question? I couldn't see.
Jack Cook.
Jack Cook, hi. So a couple of comments. So the unitary dual of a real group really can be studied entirely on its identity component. So in a sense, I could only be, I could just talk about connected groups, but there's something magical about the class of groups where G is the real, you take the real points of a connected complex group. So those groups the real groups can be disconnected. So for example, if you take the connected orthogonal group and you take the real form SOPQ, it has two connected components. But that's a very mild kind of disconnectedness. And one of the things that happens in the theory is that disconnectedness is really, really hard. And you have to, if you tried to prove theorems about general disconnected groups, you'd probably fail. And that's the reason that we stuck to this class of groups from the very beginning.
Other questions? How big a computer do you have to ask for to deal with these last four representations?
Well, I was hoping that Stephen Miller was going to interrupt or was going to send me an email before my talk saying that he'd succeeded in calculating these because we're close. I believe Steve is running these calculations on a computer with about 900 gigabytes of RAM, and maybe that's enough. I should say that the software is constantly evolving. Mark Van Leeuwen, our amazing C++ programmer, has recently improved the software, so it's quite a bit faster. And so we're hopeful that we can get these last four. Actually, I should say perhaps it's fair to say Steve's hopeful that we can't, because then he'd really like to find them using number theoretic arguments.
Steve spends half his time asking Peter Sarnak for help and half his time asking these giant computers, and it isn't quite clear who's ahead.
Jeff, so can I ask some question?
Sure.
So you mentioned, so you need a table for Springer correspondence?
Yes.
So how to say, so if you want to do in general, or if you don't want to use table, what do you need?
That's a good question. So the issue is that the Springer correspondence gives you a map, excuse me, taking a complex nilpotent orbit to an irreducible representation of the Weil group. And it's computed in terms of some cohomology of the Springer fibers, which is something that's not readily accessible. But people have computed these things for simple groups. There are a finite number of nilpotent orbits and so on. So you can look up these tables in various places, Carter's book, for example. But the problem is that we need them for a general reductive group. So a typical thing, so you might have a group with several simple factors, and well, it's a little bit cumbersome, but basically you build them up from the tables for the simple groups. And so if you need to compute the Springer correspondence of an orbit of a non-simple group, you break it up into its simple factors and use the tables. And I hate doing that because it's very coordinate dependent and you have to watch out for outer automorphisms. And that's the kind of thing that we assiduously avoid doing in the Atlas software. But this is one situation where we haven't found a way around it.
I think the point is that there's an algorithm, I can't remember who it should be attributed to, which starts with a root datum and produces a finite list of dominant co-weights, which are the sort of H parts of all the nilpotent orbits. That's, you know, there's a description from the 1970s, I think based on Bala-Carter ideas, that tells you how to compute with a root datum and get a list of nilpotent orbits. And that's what Atlas does. So what you need to have the Springer correspondence is a corresponding calculation of a list of the irreducible representations of W. And there isn't anything, as far as I know, so nice for that. You could write an algorithm that says, look at these symmetric powers of the standard representation and decompose them and order the irreducibles you get in some fashion. And you could make a list of all the irreducible representations of W. Atlas does not do that. But even if you had some way to specify this list of irreducible representations of the Weyl group, then there's the question of how you make them correspond to these nilpotent orbits. And well, this was done by all sorts of clever mathematicians in the 70s. And I would say it was a collection of ad hoc methods, definitely case by case. And I don't think it's easy to point to something to say, here's a general algorithm that does this.
David, I think, can I say something?
Please.
Hello?
Yes,
Go
please.
ahead, George.
Yes, I think if I'm not wrong, there is such an algorithm actually. It's in fact, I might be wrong, but I think I have this paper with Jiwei Yun, which is maybe one. It's an archive, but I think that paper has such a thing. I think.
Wonderful.
I think I might be wrong, but I think that's what it has, if I remember correctly. Yes.
Good.
So it's a way to define Springer correspondence to recover it without geometry. That's the point. So there's some pure algebra. So you don't. Yeah. So I think that's a thing used. Yes.
Sorry, George. Who's this paper by?
By Jiwei Yun and myself.
Ah.
So in order to understand it, we just need to get the paper and a C++ manual.
No, paper is on the archive.
I understand. Yes. Oh.
Say, Jeff?
Sure.
So, given that computer power increases exponentially, according to somebody's law, can you make any predictions about the Atlas project, say over some period of time? I mean, aren't certain calculations going to become possible given the evolution of computer power?
Yeah, of course. So a perfect example of that is the calculation of the Cauchy-Navier Vogel polynomials for E8, which we carried out in 2005 or 6 by with substantial difficulty. It required breaking the problem up mod p and doing it for small primes and then reassembling the answer using the Chinese remainder theorem. And since then, of course, computers have become faster and especially have with more memory. And so now this calculation can be run in a straightforward way, and it takes about 24 hours, if I remember correctly. So that's an example. And
no fires?
Not any fires yet. I forget, did we have a fire once?
Yes.
Burn Vinegar
Yes.
claimed to have set the some OSU server room. Well, fire is too strong a term, I think.
Yeah, so I'm not very good at making these predictions, Greg. I mean, one thing I can say is that over the years, we've frequently discussed buying a large computer. And we always wait because we never know exactly what we need. And the longer you wait, the more computing power you get for less money. And we've never actually had gone out and bought anything. And at this point, probably we won't, because
I do have an iPhone.
Yeah, there's David's iPhone. And there's the cloud. And so we'll see.
Thank you.
Other questions? I want to thank Jeff very much. There are many people here who have spoken in the Lee Group seminar and taught me a certain number of things. Many of you, I cornered you in hallways and dinners afterwards, and then you really taught me things. And others of you, like Birgit, I see here, it was only years later that I understood all the things that she had said. But I want to say thank you to all of you. It's been a blast. Bye-bye.
Thank you, David.
Bye-bye.
Thank you.
Thank you, David.
Thank you.
Bye.
Bye. Thank you.
Thank you, David.
Thank
you.